This video presents the collaborative research work between the University of Strathclyde and the Iberdrola Innovation Middle East on the design and development of a power hardware-in-the-loop interface to test the grid-forming converter with black start capability. Driven by the target of decarbonization, distributed generation has been widely deployed in the modern power industry to reduce the carbon emission of primary energy resources. The advancement of emerging novel power electronics techniques stimulates new pathways to enable higher penetration of distributed generation in the power grid. Power converters interfacing the key distributed energy resources to the power grid present a remarkable wide array of ancillary grid service provision capabilities. Grid-forming converter can establish a stable and controllable voltage on its output terminal without requiring an external angular reference. This attribute enables the grid-forming converter to be a candidate for providing black start service. Comprehensive investigations of the candidate grid-forming converter, designed for black start service provision under various operating conditions, are crucial before its final deployment. However, a mathematical modeling-based digital simulation cannot thoroughly represent the dynamic behavior of the physical converter. On the other hand, it is impractical and inefficient to go straight to laboratory-based pure hardware experiments in the megawatt scale. The motivation of this research is to address the limitations of pure software simulation and hardware experiments by developing a power hardware-in-the-loop interface with flexible power configuration and novel scaling and compensation techniques, which is dedicated to the grid-forming converter testing. As shown in this video, the system under test is divided into two subsystems. System 1 represents the real-time simulated power network. System 2 represents the physical grid-forming converter. A current mode power amplifier is employed to interface these two systems by syncing or sourcing current to the converter. This enables the dynamics in the real-time emulated network to be replicated to the physical grid-forming converter. The converter output voltage is measured and transmitted to the real-time simulation system through a controllable source, thus closing the simulation loop. The detailed system modeling, scaling and time delay compensation, and stability analysis are elaborated in the referred paper script. This research work was carried out at the internationally recognized Dynamic Power System Laboratory, hosted in the Technology and Innovation Center, that is strongly positioned to deliver novel technique through its high-quality research capability. Experimental setup. The real-time emulated network was hosted in the real-time digital simulator, where the emulated black start scenarios can be triggered in real time. The grid-forming control scheme was implemented in triphase 90 kVA converter. The control output will be employed as the command for converter modulation to establish a controllable output voltage at the AC output terminal. The grid-forming converter is coupled with a triphase 15 kVA converter with LCL filters. This power converter syncs current to grid-forming converter. This converter bridges the software and hardware and closes the simulation loop. Thanks IES for organizing this SYPA contest.